Hi, everybody. So now we're going to sort of move away from the solid constituents of rock, so like how rocks are formed from cooling magma, and talk about what rocks do in general when they're exposed at the surface, how they're deposited, how they're eroded, and what happens to that solid material once it's been exposed to the surface over time. Okay, so once a rock is cooled from a magma, an igneous rock, and here again, it could be extrusive igneous rocks like gabbros or rhyolites or um, andesites, uh, or it could be granites and gabbros and diorites, doesn't matter, but once it's exposed to the surface, those chemical constituents that are locked up in those rocks, so the chemical makeup of those rocks, begin to interact with the atmosphere, and as such, the atmosphere, either through wind or water or uh, solar radiation, I mean, all sorts of things sort of act on these rocks, and it begins to break their structures down, okay? And then those things become sediment. And sediment, because of the systems that exist on the surface of the earth, uh, those different systems will erode and transport that rock, and that sediment becomes first deposits of sediment and then becomes rock over time. So once rocks have been exposed to the surface over a period of time, there are two main forces or mechanisms rather that act upon them. As the atmosphere, whether it be rain or ice or wind, as those things begin to act upon these rocks, breaking down the chemical compositions of these rocks, because remember, they formed in a place where there's certain temperatures and depths where these minerals and the rocks that are formed from these minerals are happy, so to speak. Once they're at the surface, they're just being acted upon by these forces, and they eventually over time will break down. As they break down, there are two main processes that sort of act on these rocks and create what we call sedimentary rocks. And those two processes are weathering and erosion. And this is very important here, definitely commit it to memory. Weathering is the mechanical disintegration or chemical decomposition of those rocks as they're exposed to the surface. And this is because as the atmosphere, air, temperature, water, all these things are interacting with those rocks, they begin to break down into sediment that basically, through gravity falls down to the bottom of an outcrop, let's say, or, it'll fill river valleys, or it'll, be transported by wind and it'll settle in a certain spot. And when that happens, you get sediment. So sediment is any product of decomposing rock that forms into small sort of granular components, I guess, that collect in a certain area. So that's weathering. Weathering is the actual breakdown of the rock, whereas erosion is the removal and transportation of that material, right? And so here's where we start to get into atmospheric and surface processes that remove and transport that material away. And that can happen through wind erosion, water erosion, glacial erosion, or just gravity, like stuff can fall, move down a slope into like a river or a stream or something, and then be transported in another way from there, right? And I encourage you to click on these links and kind of look at some animations of how these two processes are different. But the main takeaway here is that weathering is the actual breakdown of the rock. Erosion is what happens to that material after it's been weathered. So let's dive into weathering a little bit. So weathering which is the first part of the formation of a sedimentary rock. Weathering is where rock has been exposed to the surface. It could be a igneous pluton here that's been exposed to the surface through uplift and erosion after it formed in the crust somewhere, or maybe at a mountain belt or something like that. It starts to break down. And it could also be a sedimentary rock that formed prior and has been exposed for whatever reason. It also starts to break down. Metamorphic rocks, same diff, like start to break down. And as that happens, as this rock is being exposed to the surface and being, forced to interact with wind or water or ice or any kind of biological activity, that's plants, humans, animals, anything like that, it starts to break down into smaller rocks. And as it does that, the very first thing that happens is this mechanical weathering, like I say. And mechanical weathering is really just rocks being broken down through force, right? So it's not acting chemically on the rock per se. It's not dissolving certain things or anything like that. It's really just very basic mechanical forces that are acting on the rock, right? So water moving things out, or ice expanding and breaking things down, or wind moving things, or biological activity breaking things apart. That's what's happening with mechanical weathering. And we'll stick to sort of a basic idea here where we talk about water specifically breaking down rock, which is kind of the main force that's always acting on rocks. And what happens is, in the case of this pluton here, we've got fractures running all down the sides here. You can imagine water is stuck up in the atmosphere in clouds, and it eventually precipitates down onto the rock. Water runs into these fractures, right? And there it sits. It might move some material away, but it will collect. And as it collects in certain areas, eventually it will become cold. And once it becomes cold, that water freezes. And one of the great properties of water, and it's unique to water in a lot of ways, when water freezes and becomes a solid, namely ice, from its liquid form, it actually becomes less dense, so it becomes more buoyant. And fish would thank us for this, because water that freezes always freezes at the top of a pond or a lake or a river. That water doesn't freeze and then all of a sudden become more dense than the liquid form and then sink to the bottom. Otherwise, there'd probably be no fish or any kind of aquatic life, because water would freeze and then move through a water column and sink to the bottom and crush everything below it. Luckily, it doesn't do that. So water is less dense than its liquid form, and so it floats. But that means it also expands, and that's just a chemical property of water. And so once it gets down into those cracks, it expands, and so it takes up more space than it was when it was a liquid, and so it will literally break up the rock or push the rock apart. So it finds little seams and fractures in the rock, it exploits those, and then it expands when it freezes, and so it will break that rock up. And this is how we get these large chunks of rock weathering away along a slope face here, but this happens everywhere, and we call this wedging. Once that happens, that stuff all falls to the bottom, it breaks down to the bottom, and then we call that unloading. And that's just the gravitational movement of the rock as it falls away from the spot it used to be in. Then we can have biological activity, like we see down here in the bottom right, where you can also imagine a seed coming from the top of a tree that's fruiting. It falls down into these different little crevices and cracks. It might find some nutrients, like some soil or something. It takes root, And as it grows, it's also expanding, right? Because the base or the root of that plant is expanding. And over time, that will also weaken the rock and break it apart. And then we can also get mechanical weathering from any kind of collision of grains as it's falling. So you can imagine rocks are falling down off the face of this big pluton here, this big mountain that's being exposed. And then, as they're falling down the slope and running into each other, they'll break up into smaller pieces, or stuff will fall and be deposited at the base here, and then other stuff will fall after that, run into it, and it just, just breaking things in half. But I want you to think about this as like sort of, uh, you know, large scale sort of breaking up of rock. And another thing that happens during weathering is chemical weathering. And this is where the rock starts to break down on a more compositional level. And this is where the internal structure of the minerals are being weathered. And this involves earth materials like rock and atmospheric materials. So air, water, carbon dioxide. This is where just the chemical components of these different materials, because of their chemistry, i.e. their charge, maybe they're positively or negatively charged, they're moving, so there's some kind of force there, but it's acting upon the rock on the mineral level, where water comes in and it's, let's say, uh, uh, electronegative, right? Like it's polar in the fact that because of its atomic structure, water would have a preferential negative charge. It wants to bond with minerals that have a positive charge. And so as it's moving through those rocks, any minerals that have a sort of slightly positive charge are going to want to bond with the negative charge of water. And that's what makes water sort of the great eroder, right? It's sort of the great dissolver. It moves through things, and anything that has a positive charge, it's going to start to bond with that stuff and dissolve it. And so here, I want you to think about chemical weathering as really like it's dissolving different minerals in the rock, and it's going to dissolve those different minerals at different rates based on the chemical properties of those minerals. And here's a quick reminder of where we are in the rock cycle. So, we just learned about igneous rocks. So here's the igneous rock portion of the rock cycle, where you've got the intrusion of magmas down here in the crust. They slowly start to cool, and they form these plutons. Eventually, those plutons are exposed to the surface as mountain ranges or some kind of exposed rock. And then the atmosphere starts to act on it. And here at the top, we see sediment being formed. So water and air are moving through the rocks here, and that stuff is starting to move down, right, because of gravity. And it's weathered to sediment, and now it's moving down through erosion into these areas of low topography, where they're settling down as sediment, and then that sediment builds up over time. And as it does, more pressure is being exerted on that sediment, and eventually it will lithify into a sedimentary rock. So we're in these like two kind of portions here, based on the rock cycle that I've showed you before. And then, we could get some metamorphism after that. These sedimentary rocks could weather into more sedimentary rocks because they're just becoming sediment again, or they could get subducted all the way after this process and become, fully melted magma again, and then become igneous rocks after that. So again, this cycle it perpetuates itself, but you can skip different steps based on how long things are exposed to the surface and whatnot. So for the formation of sedimentary rocks, we've got kind of three main processes that happen. Like I said, you have the weathering, which produces the raw materials for sedimentary rocks. And the products here, we would say, are rock and mineral fragments, right? Like those rocks are being broken down by atmospheric processes and gravitational processes. And so they're just sort of the raw materials of either either a weathered out mineral or a weathered out rock. Then atmospheric processes begin to act on those things and move them around. And here we get transportation, and that's gravitational and erosional agents that, the main driving forces there are wind, water, and ice. They move that sediment, again, being dictated by gravity. They move that sediment into a certain area and deposit them. So there we have the product, which is sediment. So weathering produces rock and mineral fragments, but we don't call it sediment necessarily until it's been transported. Once it's been transported and deposited, then the lithification process begins. And that's where you get sediments moving down into areas of lower topography, and those will get buried by subsequent layers of sediment. And the pressure exerted by that overburden of sediment produces compaction and eventually cementation and lithification. And here, let's see if I can get, yep. So here we get individual sediment fragments, mostly in the form of minerals, because oftentimes atmospheric processes will break things down to their sort of most basic constituents, right? Think about olivine grains or quartz grains or something like that, mostly in the form of like sand or mud or something like that. They'll deposit in a certain area and they'll get lithified into rock based on the pressure and cementation of the weight above them, right? And so we often get sedimentary rocks that are really rich in calcium, or sedimentary rocks that are really rich in quartz, or sedimentary rocks that are really rich in iron oxides, among other things. And one thing I think is very valuable to point out here is that most of this portion of the rock cycle, so most of the sedimentary rocks that are formed, are all happening at the very outermost layers, right? Because what's important about sedimentary rock formation is that it has mostly to do with environmental interactions. So it has to be atmospheric or surface level forces acting on these rocks and breaking them down and transporting them around that produces sedimentary rocks. Like sedimentary rocks do not form deep in the crust. They don't form in the mantle. They don't form anywhere near the core. They don't even form like, deep in the crust. They're absolutely happening at the very uppermost portions of the crust, where rock is interacting with air and water. And two things that they tell us, because they're telling us a story about environmental conditions, is that they record surface conditions at the time of formation, right? So they're taking the environmental conditions, whether it be lots of topography, so fast moving rivers because they're moving down a higher slope, or they're forming in a big ocean basin, so we know that it's a big open flat area where, but in the ocean where they can collect in a certain way. So sedimentary rocks really are the most important rocks when we're talking about what kind of stories they can tell us about paleoenvironments or ancient environments. And also, as they do that, they get lithified and preserved in the rock record, and so they can help geologists sort of reconstruct the details of the Earth at that little snapshot in time. So we can learn something about the geologic and biological history of the Earth at that one moment, based on chemical constituents, fossils, obviously, all sorts of things that can help us understand what was happening at this one place at this one moment in time. So for a deeper look into the sources of sedimentary rocks, or the sources of sediment, generally sedimentary rocks are made of sediment that are sourced from both different particles that have broken down over time due to weathering, and we call this detrital sedimentary rock. So sandstone, mudstone, things like that, where larger exposed rock, I mean, from the mountain scale down to just a boulder or something like that, starts to break down through different weathering processes that I've already mentioned. And as it moves through a river system, any kind of a water system, or it might be blown around by air, anything that pushes these rocks around and causes them to collide together and break down into smaller parts, we call that detrital sedimentary rocks. And that's from the word detritus, which basically means like kind of leftover portions. So I think of this as a sort of cascade of, like, you start with large rocks, boulders the size of houses even sometimes, that over time just break down into smaller and smaller parts. Each one of those is a detrital sediment. And then we also have chemical sedimentary rocks, which are like I talked about in the case of limestone. You can have sediment that's formed from, parts of organic shell material, or any kind of, it can be organic, can be inorganic too. It really just has to do with certain things like calcium carbonate, for example, from either shells forming and breaking down and falling to the bottom of ocean basins or river basins or lake basins, or it can be stuff that precipitates out and becomes solid inorganically based on just what's dissolved in water. When that stuff becomes solid and falls to the bottom, it's also being deposited through not erosional factors quite as much, but still being deposited. You can get, like I said, chemical sedimentary rocks from that. So the two main ones are detrital, like I say, which is big rock broken down into small rock, moved and deposited, or rock that comes out of solution that's been dissolved prior and comes out of solution as a solid and also gets deposited. And for detrital sedimentary rocks, we have to really think about what minerals, based on what we've learned about minerals and where they form, which ones are more stable at the Earth's surface. And I'll remind you here that we talked about the Bowen's reaction series and how olivine and pyroxene and certain minerals, they like to form at deep temperature or deep pressures and at high temperatures, and so they're preferentially stable under those conditions. And so once they get to the surface, they like to break down really quickly. And then you have things like quartz or certain feldspars, like the potassium feldspar or K feldspar, that are very happy at the surface of the Earth. They're stronger, basically. And so for detrital sediments, we tend to see a lot of quartz, clay minerals, limonite, hematite, feldspar, calcite, gypsum, halite. These are things that are in solution. Maybe if you have a warmer, groundwater that's been, dissolving these materials, a magma, let's say, that's moving up through the crust and it's absorbing these materials. Once it cools on the surface, it starts to cool at those lower temperatures. And so at the surface of the Earth, we get a lot of quartz, a lot of feldspar, a lot of amphiboles and stuff like that. And that stuff will break down into smaller constituents of those materials. Whereas olivine down here, Let me see if I can turn on my thing again. Down here, olivine, like limonite, hematite, things like that. Lots of iron-rich or magnesium-rich materials. Still silicates, but but bound by atoms that are not as comfortable at the surface. Those might break down much faster compared, relatively speaking, to quartz and feldspar mainly. Most of the sediment that we see in detrital sediments are composed of these kind of happier elements and minerals at the surface. And so we see a lot of quartz kind of sticking around and getting smaller and smaller. I would point your attention to the sand we see like in Lake Michigan, let's say, where most of that sand is made up of quartz and feldspar. Those are, again, more comfortable at the surface. And so a lot of the sedimentary rocks that we find are composed of these more felsic materials. So when it comes to detrital sedimentary rock names, we tend to classify these based on the size of the different sediments that we find that have been, conglomerated together into a certain sedimentary rock. And the largest size we call a boulder, and that's anything above about 25 centimeters or 256 millimeters. And you can imagine, based on the size of a 1 foot ruler that you use here in class, that 25 centimeters is about that length or so. It's about 12 inches. And then we grade down from there. So anything from 64 centimeters or about half. So think about the size of your your foot, or maybe 3/4 the size of your foot if you have a big foot, then up to 256 millimeters or 25 centimeters, that's a cobble. And then you got pebbles and granules grading down from that, and all of those make up a gravel. So anytime you see a sedimentary rock that's made up of class about that size, we call that a gravel, and the rock that forms is a conglomerate or a breccia. And then we have sand, which is about a 1/16 of a millimeter, so super small, to about 2. And we all kind of know what sand is. We've held it in our hands, we've seen it. And that forms sandstones. And then any particulate smaller than that, even though they might be still made up of quartz and feldspars and different clay minerals, micas and biotites, that stuff's broken down really, really small. And then those are in the sediment form, they're muds, but we would call them shales or mudstones. And I want to point out that each of these over here, conglomerate, sandstone, shale, and mudstone, are all in your sedimentary rock kits. And so we'll break those down a little bit further later on in the lecture. And so this leads me into the attributes of detrital sedimentary rocks. So the main things we look at when we're looking at detrital sedimentary rocks is particle size, like I just mentioned. So how big are the different particles that were consolidated together and lithified, whether they be conglomerates or mudstones, right, at the small end. We also look at a thing we call sorting and rounding. And this basically gives us information about how far that sediment moved, what was moving that sediment, and how far away that sediment traveled from the source of that weathering rock to where it was deposited. And the class sizes, here you can see illustrated there on the left. We would have kind of gravel sized, right? So we've got boulders there, boulders, maybe some cobbles, and that would be a river. Imagine a river where you see kind of larger boulders, like you could run across them. Maybe you pick one up, it's the size of a baseball or something like that. We've all seen, hopefully, maybe rivers like that. We don't have too many of those here in Michigan, maybe in the UP, but we have those, across the continent. And then we have here in the middle, we would have different grains of sand. And so at the coarser end of that, on the bottom here in this column, we see sand at the most coarse end, at sort of an intermediate end, and then at a fine-grained end. And we've probably all seen sand like this. Sometimes you're walking on a beach, and the sand grains are maybe 2 millimeters or so, maybe a millimeter, 2 millimeters, like big enough that it makes you can hold it in your hand and kind of see the individual minerals, usually quartz and feldspars. And then at the medium end, I can think of some sands that we have out at the lake shore in Ottawa County. Usually you see this kind of sand being brought in from quarries and stuff if they're building a beach that where they have to bring sand in. Sometimes it's this kind of medium grained sand. And then the real fine sands are the ones that we see that sort of naturally deposited along the lake shore, and we see these at the ocean. I mean, you can see all three of these types, but we can all kind of imagine what like a real fine sand would look like. It's real soft, it's real fine. And I want you guys to think about, kind of what controls the size of these clasts. Because remember, all of this rock is being sourced from somewhere else. It was solid rock at one time. And here we can imagine, the rock source being somewhat nearby. And here, maybe it traveled a little further, and then here it traveled further still. Because remember, these things are breaking down as they travel, like along a river system. Let's say they're breaking down into smaller and smaller pieces. So if you think about this a little bit, and we think about the different sizes of the clasts that are being moved around by a river, a lot of that's going to be dictated by the energy present in that river. So what's the velocity and water volume of that river? A river that has lots of energy, it's fast moving, there's lots of water in that stream system, it's moving through really fast, it's going to push rocks through it that fall down in, that have broken down from, the cliff walls around a river or something like that. It falls down into the valley. Once that happens, the energy of the river is going to push different sizes through preferentially. So if we have a river that moves really fast, it's going to push all the sediment. You can imagine just a river that's all churned up, and there's lots of sediment, and it can push pebbles, maybe even boulders or cobbles of all different sizes. It's going to have enough energy to push that stuff down. And that stuff's going to move down the river system. And eventually, as the river loses energy, as it gets flatter and flatter as far as the topography goes, the river's going to slow down. It's not going to have as much energy to push different sizes of clasts around. And so as that happens, the energy in the river at that one moment, maybe that energy is not going to be enough to move this little pebble or this pebble, but it's going to continue to move the finer parts along. And so that stuff will settle down with the bigger class, boulders, gravel, all that stuff. All that stuff's going to settle early in the river system when there's more energy. And then eventually, as lower and lower amounts of energy are available in the river system, or lower velocities and less water volume in the river system, then this stuff is going to stop being pushed down the river, and it's going to settle into the riverbed. And then eventually, by the end of the river, the only thing that the river's strong enough to continue to carry is going to be this smaller stuff here. So at the beginnings of rivers, or at the top ends of rivers, if they're flowing downhill, at the top we're going to see less sorting and more larger class. And as we move down, we're going to get down to eventually the only thing the river's moving is this finer grained sediment. So those are the main controls. Also, we have shape. So you can look at different sedimentary rocks, and if you have sediment that is formed here on the ground, eventually that's going to get buried and turned into rock over time. And I want to point out here, all sedimentary rocks are formed from these kinds of processes. Like if you're walking through the desert and you're kicking rocks around and stuff like this, right? You're kind of walking around these big boulders and you're kicking little bits of gravel and pebbles and stuff around. over geologic time, eventually this area is going to be covered by an ocean, a shallow sea that's risen up there. All this stuff is going to be buried eventually. If it's not buried, it's going to be exposed to the surface, and it's going to be weathering and eroding as part of that cycle, that sort of exposed cycle where it's exposed to the surface. But eventually all this stuff will be covered up with ocean. And then that stuff is just sitting there, and other sediments are going to be coming in and burying these sediments, right? And this is how geologic time is recorded in sedimentary rocks. And as these rocks move through, different river systems, they get, moved around, and sort of they bump into other sediments and things like that. And so over time, as they break down off the mountainside, they're just going to be angular and sort of jagged with sharp edges, because that stuff's just weathering based on fractures in the rock. So it's going to come off in these all sorts of different shapes. But as it moves through river systems, that stuff is getting polished down as the friction between different grains is moving through a water system, and we start to get a little bit of rounding on those. And eventually, if rocks are moving through a river system long enough, they're going to start to get so rounded that they're almost like baseballs or golf balls. And when that happens, that tells us that this river system had enough energy in it. It was a fast-moving river that it was able to take rocks like this that are angular with sharp edges, etc., move it downriver enough that it continues to work the rocks into a rounded shape, and further enough even that it completely rounds the rocks. And in the case of these large rocks, when we see a rock that's large, like maybe the size of a grapefruit, it's rounded and it's large. So we know that it was big to begin with. It's moved far enough that it's been rounded almost to the point of being perfectly spherical. And that tells us that this was a super high energy river, because it carried these clasts for a long time. They were large in size, and they were in the river system long enough to be rounded. So here's an illustration of that. And here we see the source of the rock, right? So this is just an outcrop that's being eroded away, and those rocks are breaking up. And you can see here that they're not rounded at all. They're very much, angular, big chunks of rock that's fallen down. As they move through a river system, they start to round out, right, and get weathered down to these round shapes. And then further down the river, they're smaller, and they're still kind of rounded. And the controls on that basically are, how far from the source are you, and are you rounded, and are you large or small, right? So if you're further from the source, you're going to be smaller and more rounded. If you're closer to the source, you'll be slightly rounded and larger. And if you're close to the source of that river, you're going to be less rounded and very large. So the controls on this are time. How long is that rock in the river, right? Or in that body of water that's moving. The size of the class tell you the strength of the current in that river. And then another thing about size is the agent of transport. And here I want you to think about, could wind also move rocks around? Or sediment, I should say, around. And when you see a uniform small distribution of sediment, like we see in sand dunes, let's say, a good example would be the Sahara Desert, or parts of the Southwest United States. There we don't have any running water, we have wind, and wind also blows sediment around. But I want you to think about how much wind can actually move different sediments of different sizes and different shapes. And now let's transition into the actual rocks that you have in your kit, and how the things I mentioned before, like sorting and grain size and those sorts of things, and mineral content of different sedimentary rocks, can tell us something about the environment in which they formed. So we're going to start here with a shale or a mudstone. This is one of the rocks, sedimentary rocks in your set. And what's important here to point out and important to keep in mind as we go forward is that when you're looking at any sedimentary rock, maybe you're looking at the best representation of what was happening on the surface of the planet during the time of that formation. Okay, so it tells us a lot about the environment, and oftentimes that's based on, here we've got this beautiful fern fossil over here on the right that tells us we were in a certain environment based on, you know, the temperatures and the latitude and the place on the earth where these types of things grow, right? And you know, we make certain assumptions about nature in the fact that we think that the same rules that apply today applied to back in the day, right? So a fern growing on the planet today grows in a certain environment, and we imagine that if we see a fern fossil in a mudstone, we assume that that same fern grew in the same types of environments that we see ferns growing today. Okay, so mudstones and shales often contain many, if not most, of the terrestrial fossils that we find. So dinosaur fossils, fern fossils, tree fossils, other plants, other animals, things like that. Usually when they're in a mudstone, it means that they formed near the shore, like maybe in a lagoon or something like that, out in the ocean, but close to shore, or they formed on land in like a swampy environment or something like that. And so this rock here tells us a pretty good story about the environment of formation. If there's these small particulates here, we know that this water didn't have a lot of energy, right? Or it was at the end of a river system that had a lot of energy, but at the point where all this sediment was deposited, there wasn't a lot of energy anymore. And we know that from a number of different ways. We know that the grain size is really small in this black portion here, right? This is really, really fine, like silt or mud, really, really small particles. So it's at the end of the journey for any kind of sediment. It's been broken down to its smallest parts, basically. And we know because of the color in this case, that because it's black and it's got these plant fossils in it, we know that this was probably the result of the settling of really fine particles, like I say, in really non-turbulent settings. And what do I mean by non-turbulent? I mean the bottom of a swamp, the bottom of a really calm pond, something like that. And you can imagine terrestrial plants, like plants that grow not in a marine environment or not in an aquatic environment, so plants that grow on land, their branches are going to fall. They're going to get washed into said pond or swamp. They're going to sink to the bottom, and they're going to settle in the sediment at the bottom. And we've all probably stepped in a swampy spot at some point in our lives, and when you try to pull your leg out of there, your leg is so stuck in tons of mud, and it like might suck your boot off or whatever. And that's the environment that this thing fell in. And how do we know that? Well, we know the water wasn't moving because of the size of these grains here, but also the color, it being black, tells us that this was a rock that formed from sediment that was deposited in an area where it was deep. There wasn't a lot of available oxygen coming from a current or moving water. So it was just deep in some kind of swampy area. And when you have sediment that's deposited and sits for a long time at the bottom of a swamp or a deep pond that's not moving, it's not turbulent, you tend to get what we call anoxic environments. And anoxic, A-N-O-X-I-C, means not a lot of available oxygen. So that means a real still, deep, swampy environment where lots of bacteria is allowed to grow. It's mostly feeding on methane and things like this. It's not getting a lot of available oxygen. And so these plant parts, they fall down in there, they settle in that mud, they eventually get buried, that water dries up and then it gets buried and then it fills with water and it gets buried and blah, blah, blah. And eventually enough stuff deposits on top that it gets pushed and squeezed and lithified into rock. And then that's a little snapshot of that area. So we know that this rock formed in a swampy area. Now, one thing to keep in mind while I'm staying on this slide here is that the environment on the surface of the planet changes over time. And so the water levels in this swampy area could have gotten shallower, which means more oxygen would have got down in there because there's less water for the oxygen to travel through. And so we might get a slightly different color of this mud because it's not oxidizing in the same way or not oxidizing in the same way. So oftentimes these shales and mudstones, they split into these layers, right? Where you get different chemical compositions of the different sediments as they're being laid down. But one thing, again, before I move on, is I want you to keep in mind that when you see a black rock, a black mudstone with lots of plant debris, this generally formed on the surface in a real swampy environment, so not a lot of moving water, right? A lot of stagnant water. So to dive a little bit deeper into shales, shales are deposited generally in lakes, rivers, floodplains, lagoons, and then sometimes in deep ocean basins where the wave action from the ocean is more up on the top, on the surface of the ocean, but deep down in the ocean basin, you're not going to get a lot of movement. So it sort of mimics the environments we see on land with like certain ponds and swamps where the water's not moving a lot, it's deep, and so it's anoxic, lots of bacteria, lots of real fine sediments, etc. It tends to be black, which means it's organic rich, so stuff falling down in there and just piling up, lots of organic materials, right? Animal fossils, plant fossils, mostly plants. And it's low oxygen, right? When it's that black color. And that's because of the bacterial reactions that are happening, right? Certain bacteria just favor low oxygen environments. They tend to turn the rock black. Then we have red or green. Red tends to mean that we've got oxidizing iron, right? So that sediment is iron rich. Sometimes it can be green, also iron rich, and that's more, again, of a bacterial reaction to iron rich minerals. But it could also be traces of other metals, right? We could get like a greenish shale, and that tells us that it formed in conditions where there might have been iron, there might have been copper, there might have been silver-rich minerals, aluminum-rich minerals, etc., right? And that tells us something about where that sediment was sourced, how far it traveled, based on how long iron and aluminum and different things oxidize and break down in a water system. We can also get the compaction, right? So clay particles, if they're forced parallel and they're tightly packed with little pore space, that tells us something about the amount of energy in a river system based on how tightly packed those particles are together. And one really important thing about shales is because they're such small grained and they pack so tightly together, because they're really rounded and their surface areas are really small, they can pack really close together. Think, powdered sugar versus, coffee beans, right? Powdered sugar, there's going to be a lot more tightly packed. And if you were to pour water into powdered sugar versus pouring water into a pile of coffee beans, the water's not going to move through the powdered sugar nearly as well as the coffee beans, okay? And so shales tend to be, because they're so finely grained and finely packed or tightly packed, they tend to not allow a lot of fluids to move through them. And this is what we call an impermeable barrier. Permeable means the ability for fluids to move through something. Impermeable means that fluids can't move through them. And oftentimes when groundwater or rivers or anything are moving through different types of sediments, uh, they'll soak into a sandstone, let's say, or they'll soak into a gravel. But when they hit an impermeable barrier like a shale or a mudstone, they tend to just flow over it, right? They can't soak in. So then we also have sandstones. This is another rock in your kit, and these are sand-sized grains. And I'll have you refer back to the slide about grain sizes to kind of get a sense of what a sand grain size is. It's about a 1/16 of a millimeter to about 2 millimeters. And it's predominantly made of quartz. Again, I'll remind you, quartz is the most stable at the surface of the earth, so it doesn't chemically break down the same way an olivine would or a pyroxene would or something like that. Quartz sticks around, but because of mechanical weathering, it's going to break down. It's going to be broken down from its source rock, whatever that may be. It's going to be carried by rivers and wind and wave action and all sorts of things. So it's going to break that rock down into smaller and smaller pieces, but it's quartz, so it sticks around for a long time. That's why most sand on the planet is quartz sand, right? It's how we make glass. Glass is made out of quartz. We just melt down sand and then form it however we want. Like when you're looking at glass in your windows, that's all silica, right? It's all silica and oxygen. It all comes from quartz, right? But we can melt it down and form it into whatever we want. And we use that because it's stable at the Earth's surface. It's hard. It sticks around a long time. And so does sand, right? Some sands have, if you pick up a pile of sand in your hand, like let's say at Lake Michigan, that sand is made up of tiny, tiny pieces of quartz and some feldspars and trace other minerals. You can even find garnets in there and things like that. That stuff's been around forever. It probably started as an igneous rock, maybe billions of years ago, broke down into sand, formed a sedimentary rock. That sedimentary rock then got weathered into more sediment and became a different sedimentary rock, or it got metamorphosed and became a metamorphic rock, or it was part of oceanic crust that subducted down into the mantle, melted, became magma again, and then that quartz got reincorporated into a new magma, right? And just became silica in another magma chamber. So sorry, I got distracted by the rock cycle there, but that's the idea here, right? When you hold that sediment in your hand, that's stuff that's been recycled over and over and over. And the reason we see mostly quartz on the surface is because it likes low temperatures and pressures to be solid and stable. When it gets buried and lithified, it becomes sandstone. And like I said, it can have, feldspars, it can have some micas, some iron minerals. Many of you maybe have been to Lake Michigan and seen those like big streaks of black along the shore. I always assumed when I was a kid that was, oil or something, maybe from boats or something. I don't know where that came from. That's actually ferromagnesian minerals, usually magnetite. If you go out there, get a bunch of that black stuff, bring it home and dry it out and hold a magnet to it, it'll all stick to that magnet. A lot of it is magnetite with some titanium and other things. And then sand can also have some rock fragments. So a lot of sands, like I said, can be coarser grained to fine grained, and sometimes you get bigger fragments of rock. Smaller pebbles can be incorporated into a sandstone, and they're often angular if that sediment was sourced close to, or if it was deposited rather close to where that stuff was sourced from weathering rock, or if it traveled a long time through any kind of a current, it can be rounded. And here I want to revisit sorting, because sorting is really like, what's the energy of the agent that's moving that sediment in that spot at that time? Okay, so we can think of different grain sizes and different materials of different sizes being sorted throughout an entire river system or throughout an entire system of different strengths of wind, let's say, right? There might be wind that's really strong in one area that's able to move lots of different sizes of sediment around because it has enough energy to push that stuff around. But then you think of an area where the wind is really light, it might just be blowing the very finest sort of dust-like particles in that spot and moving them to a different area. And as that winds down, eventually that stuff just settles there. So sorting really tells us where we're at in those systems, and that's wind or streams or waves, right? And so oftentimes in a sandstone, when we see a sorted sandstone, if we see it's well sorted, that means that most of the grains are the same size. And if it's poorly sorted, the grains are all different sizes. And windblown sands are better sorted, right, than different sands deposited by waves or streams. And this is because winds tend to have the least amount of energy to move particles across the surface. And so if you see well-sorted windblown sands, that's because the wind is going to preferentially deposit much more finer grained stuff because it doesn't have the energy to move larger stuff. So it leaves the larger stuff behind, starts to sort the medium stuff. That stuff deposits in one area, so it's mostly medium stuff in that area. And then it continues to blow it until it deposits the finest grained stuff in one area, so it's mostly fine grained stuff in that area. So wind-blown sands tend to be better sorted, just because the amount of energy in a wind system is more drastic than in streams. And the better sorted it is, the longer the transport time of that sediment. And so during transportation, whether it be by water or wind, like I said, these particles tend to lose their sharp edges because they're colliding with each other, they're colliding with the banks, they're being rounded by the water or the wind itself, and so they become more rounded. And rounded grains are almost always transported by wind or water. And the more rounded they are, the longer they were being transported. So when you see very angular grains, right, so lots of sharp edges, lots of corners, not as rounded, these fragments were transported much shorter distances, okay, usually by water or wind. Or they could have been transported long distances, but they were transported by glaciers. And I won't spend too much time on glaciers here because we have a whole chapter on it. But the way glaciers function, they're able to transport sediment, whether it be boulders the size of a Volkswagen or gravel or sand or mud. They're able to transport that stuff sometimes thousands of kilometers, just based on the way a glacier, the dynamics of a glacier and the way it moves. And another thing that's really important is looking at the mineral composition of different sandstones. So if you have long transport times, that tends to lead to the the destruction of sort of the less stable minerals that were sourced from parent rocks, right, that were weathering away. Those minerals get transported by wind or water, and if they're a mineral that cools at higher temperatures and pressures, they're less stable at the surface. And so they tend to be destroyed more quickly or break down more quickly. And those tend to be the feldspars and the ferromagnesian minerals like olivine, pyroxene, some garnets, things like that. So as sediment is moving through along the surface, like either in a river system, like through a water column being pushed by currents, whatever, or it's moving along the surface being blown by wind, the minerals that are sort of higher in the Bowen's reaction series that like to be at higher temperatures and pressures are going to break down into their chemical elements and be washed away, whereas quartz, which forms, remember, that really strong framework silicate where every silica has an oxygen attached to it, but that oxygen is attached to the silica next to it, forming this really strong framework. Um, that stuff is going to be very stable at the surface and can survive for a long time. So what does that mean? That means that sandstones where you find, grains, regardless of how big they are or how rounded they are, which does tell you something about the time of transport and the current. It also tells you if you have a lot of feldspars and ferromagnesian minerals in a sandstone, that means that that sediment was deposited very close to the source of that weathered rock where that stuff came from. Whereas if you have a sandstone that's just mostly quartz, or if you think about the beaches here in Michigan, like on Lake Michigan, most of those beaches are all purely quartz with just minor bits of olivine and garnet in it. And that means that that rock could have been sourced from very far away. And it had a long time to travel. All this stuff up here broke down, leaving just the quartz behind. And then that stuff eventually settles on a beach or settles at the bottom of a lake or an ocean and gets buried and lithified into sandstone. And the mineral composition of the rock, for our cases, when identifying different sedimentary rocks, will determine the name of that rock. So if it's mostly quartz dominant, we'll call it a quartz sandstone. For our purposes in this class, I'm happy with you saying just sandstone if you have a quartz-rich sandstone. If there's an appreciable amount of feldspar in it, it'll have mostly potassium feldspar, because remember that's the one that likes the surface more. It's the last thing to cool out of a magma. So it likes those lower temperatures and pressures. Potassium-rich feldspar is that pinkish or reddish color. And so if you see a sandstone that's reddish or pinkish in color, we call that an arkose. All of your kits have really, really deep red or almost purple sandstones. And I'd like you to call those an arkose. And then if you get abundant rock fragments, right? So you have a sandstone that has lots of rock fragments, but maybe even some clay minerals too in it, we call that a greywacke. Quartz sandstone and arkose are absolutely in your kits. Greywacke you have been thankfully spared from. So when we get to the really fine-grained sedimentary rocks, we have two types here, one of which is in your kit. The first one is a conglomerate, and that's rounded gravel-sized fragments. So gravel-sized are, 2 centimeters to, 60 centimeters. We would call a gravel. And we call that a conglomerate. And here's a conglomerate over here on the left. You can see that you got real fine-grained sands here, maybe some really fine-grained muds mixed in with that sand. But then mixed all throughout, you've got these pebble-sized or gravel-sized larger clasts, and they're super rounded. So that tells us something about the environment in which this formed. It's poorly sorted, so that means it was probably, it probably had a certain energy level, the current did. But we know that this was in some kind of a river system where the water was moving. It was able to transport these larger clasts far enough that they started to get rounded. It was probably low energy because it couldn't push these, and it couldn't push these. Because remember, when you're looking at a rock, this is everything that settled at the bottom of that water system and eventually formed into a sedimentary rock. So when it's poorly sorted like this, as in the case of a conglomerate, we know that this system, whether it be wind or water or whatever, didn't have a lot of energy, right? Slow-moving currents, or not a lot of force behind a wind current, where all this stuff wasn't getting blown away and sorted out later, the finer grained stuff. And so this stuff is just settling here. It landed on the ground and became a rock, right? We can also get angular gravel-sized fragments and this type of rock over here on the right, we call a breccia. And both of these rocks, like I say, are almost always poorly sorted. But the amount of rounding over here versus no rounding over here tells you something about how far these two rocks traveled. These rocks over here that are rounded started as rock fragments over here that were angular, but over time, as they moved through a river current, they got rounded. So this tells you that this rock formed very close to the source of the weathering, and this rock tells you that it formed very far away from the source of the weathering, right? The source of the rock that provided all these different clasts. So the environment of formation, generally for conglomerates and breccias. For a breccia, you get like steep slopes or high energy with turbulent currents. For breccias, often they're glacial because glaciers don't round things as they transport them, as opposed to a river or the wind or the shoreline of a lake or something like that. And breccia often forms because of landslide deposits. So rock weathers down off of a slope. It lands at the base of that slope. It sits there for a long time. That rock will slide eventually. You know, we get avalanches and landslides and things like that based on other geologic forces that we have or will talk about. And they tend to deposit real close to the source of that rock, and then they just get buried and lithified and become breccias. And the key here again is angular clasts, not rounded. Conglomerates tend to be, on the other hand, energetic mountain streams or strong wave action in the case of a shoreline, where those rocks are being churned and moved past each other, and they slowly, over time, their edges get rounded. And then we also have the chemical sedimentary rocks. And different from the detrital sedimentary rocks, which were pushed around by mechanical forces, right, on the surface, these are rocks that kind of grow out of a solution, similar to the way minerals grow out of a magma. Dissolved minerals or dissolved ions, chemical ions, in a solution, in this case water, as they're dissolved in that water and then that water begins to evaporate, those elements will begin to crystallize, right? And be deposited as a solid at the bottom once there's no water left. So here we've got some gypsum over here on the left, and here we've got halite or salt deposits on the right again. And so this is how the minerals form, right? Just from shallow evaporating seas. But all of that stuff can come together to form rocks, which are different collections of minerals. In this case, we've got little chunks of gypsum in larger chunks of salt or halite. But as they're precipitating out of solution, just like minerals will solidify, cool and solidify and precipitate out of a magma, these are cooling and precipitating out of an ocean, right? Out of water. And so therefore they tend to be crystalline because they can actually grow crystals as they're coming out of solution. And this is very similar to if any of you have ever seen rock candy being made. What they do there is they heat up water, and then they'll dissolve a bunch of sugar in there. And because of the heat, which isn't necessarily the case with these chemical sedimentary rocks, but I think it proves the point well. If you supersaturate a solution with a certain mineral, in the case of rock candy, it's sugar. You just heat up the water to where it can hold more sugar than it would if it was at a different temperature. Then as that cools, it starts to grow sugar crystals on a string or on a stick, and then then it's rock candy that you can eat. And because it's growing slowly out of solution as something cools, in this case water, then it can grow the crystal. And that's the exact same thing that magmas do when they're growing crystals in a pluton, as opposed to when they erupt on the surface and don't have time to grow crystals. So chemical sedimentary rocks can behave in the same way. and the size of the class of those chemical sedimentary rocks tell you something about how long it took for this stuff to evaporate, the water to evaporate, rather than cool. Because we are talking about surface water here, so it's not super hot and it's cooling. It's more just how much of that stuff is available as that water's cooling. So we have precipitation by two different things here. So we have inorganic processes, and that's the evaporation and different geochemical activity, like I talked about before. And that's just available amounts of those ions in solution as they solidify out. Will give you different types of chemical sedimentary rocks and different grain sizes of chemical sedimentary rocks. But then we can also have organic processes, right? And this is where you have water-dwelling organisms that are forming shells, and this is corals, plankton, snails, anything that forms a shell or any kind of a hard part of its body that can be preserved in the rock record or concentrates chemicals enough that they can be deposited or dissolved and then deposited, right? That's when we say they're biochemical in origin. So we have inorganic, and then we have biochemically organic. So primarily for the chemical sedimentary rocks, the ones that are in your kit and the ones that we're most concerned about on the surface of the Earth, in fact, they are the most abundant sedimentary rock on the planet, are limestones. They're composed chiefly of calcite. Remember, calcite's the calcium carbonate rhombohedral mineral that you had in your mineral sets that fizzes with acid. It reacts with hydrochloric acid. These are composed chiefly of calcite, like I say, and calcite can be formed, or limestones that are made of calcite can be formed from inorganic or organic means. And the organic limestones, generally speaking, or predominantly on the surface, are ancient coral reefs. They're shallow, warm, tropical to subtropical waters, usually about 30 degrees latitude above and below the equator, like right where it's nice and warm. Think Florida to the Bahamas to Barbados, parts of Northern Africa, the Mediterranean, just across that whole equatorial zone there. And there are accumulations of carbonate-rich shells of different marine animals and different marine sediments. And the types that we have in our set are fossiliferous limestone, which is there's a perfect example over here in the bottom right. These are some ancient Devonian, Silurian fossils. These are different kinds of bryophytes and crinoids, sort of ancient marine life. These are very common in the limestones we see in Indiana, Ohio, some in southern Michigan, but not exposed, usually just in quarries we find them because we've got a lot of glacial sediment above us that bury most of our bedrock. Mostly you see these in Ohio, Kentucky, Tennessee, West Virginia, southern Indiana, southern Illinois, parts of Missouri. Lots of limestone deposits, and they have these very distinct bryozoan fossils and crinoids, these little stems you see here, and then lots of shells of different types. We call that fossiliferous limestone. Sometimes you'll find limestones that are almost made entirely as shells. Those are much younger. They haven't compacted and lithified enough yet to become this darker limestone that we see here. They tend to be whiter in color. I say they kind of look like oatmeal, and you'll see that in your kit. They all look like just a chunk of oatmeal, like dried oatmeal, and that's called coquina, C-O-Q-U-I-N-A. And then we can get real fine particulates of limestone made of real fine calcite that will fizz under, when acid's dropped on it. But it means these different calcium carbonate organically sourced materials have been broken down through weathering and turbulence and whatnot to the point where they're almost a fine, almost silt. And we call that micrite. And that's a really tough one because it can look a million different ways, but it is a fine-grained mineral, the most fine, not mineral, it's the most fine-grained rock that you have in your kits that when you scratch it and drop acid on it, it will fizz. So acid is the only way you're probably going to be able to identify this micrite and separate it out from a couple of the other ones that are tricky. So then we also have limestones that are inorganic. And here I want to make a distinction that you can have inorganic limestones where the calcium carbonate, because of the rock cycle and the time spans involved, you can have calcium carbonate that maybe once was sourced from organic materials, shells and corals and things like that, but it's long since been recycled, dissolved, precipitated, and eventually can start to form rocks that are sourced just from that calcium carbonate coming straight from the water and not the result of any kind of shell debris or shell material. Even though it might have, like at one point came from there, it's been completely dissolved and reformed a number of times in many cases. And so we call that inorganic because it wasn't directly sourced from marine organisms. So as you can imagine, it contains no fossils, right? Even if it was once, even if the elements in that rock were once from a fossil, that fossil's long since been dissolved and reprecipitated and dissolved and reprecipitated, etc. And we call that travertine. And that's what caves are made out of. Mostly is this like, if you've ever been in a cave and seen a stalactite or a stalagmite, it's all very fine grained. It almost looks like a mudstone, right? You can't see any shells, no fossils, nothing like that. And the mineral you have in your, or the rock rather, sorry, that you have in your kit that is representative of this is dolostone. And dolostone is closely related to limestone in that it's calcium carbonate. But in this case, there's been magnesium incorporated into the crystal structure of the limestone, or the different minerals that make up the limestone, and which is mostly calcite, but with this magnesium component. And the magnesium can just tack on to this, or it can sometimes replace the calcium altogether, giving you magnesium carbonate, MgCO3. And these tend to precipitate directly from seawater, or some kind of magnesium-rich water can move through them later and dissolve the calcium and deposit the magnesium onto this carbonate polyatomic ion here. Okay, so what I want you to think about here is it's basically limestone, but instead of a calcium carbonate, it's magnesium carbonate. Okay, and so it still reacts with acid, but way less than limestone, way less than calcite, and less than micrite, which is the one we talked about earlier. But what makes dolostone is that magnesium portion. And if you scratch it on a streak plate or scratch it with a knife or with a nail and you get a fine powder and you drop acid on it, it can fizz, but not much, because that magnesium really wants to hold on to that carbonate. And so it doesn't want to form the CO2 that the others do. And now I'm going to talk about some other chemical sedimentary rocks that form from organic material. And you're going to start to see a little bit of bleed over between our minerals and our sedimentary rocks here now. But you'll remember we have chert and we have the evaporites like gypsum and halite, right? Those are microcrystalline evaporite minerals. But if they're formed from organic materials, we can differentiate them from their minerals, okay? So chert is a mineral, but if chert came from microscopic organisms that have silica shells that they grow, we consider them a sedimentary rock at that point. So depending on the environment, if it's a chert, but it is clearly deposited by organisms, then it breaks the rule of minerals being inorganic. And so we would now say that chert is organic. And if it's organic, it's a sedimentary rock. Same with gypsum and halite. If any of that magnesium in the gypsum or any of the halite or any of the salts in the halite, if any of that's sourced from bodies of water that evaporated that had organisms in them, we would consider them sedimentary deposits. Okay. In your kit, the organic evaporites is basically when plant material falls into a swampy area and it starts to break down. If it starts to break down enough that it starts to dissolve into the water, then that water evaporates away or gets lithified under pressure, then that carbonaceous residue gets preserved. And if it gets preserved and is altered by heat and pressure, then it's coal. And coal is one of the kind of last sedimentary rocks in your kit. And this is, again, carbon-rich material from organics, plants, that get slightly metamorphosed by heat and pressure. And usually they form in environments with large amounts of this plant debris, and they have to kind of be oxygen deprived. And you'll remember when we were looking at that beautiful mudstone in that previous slide, the first slide where I was talking about the rocks in your kit, that that mudstone was really black because of the anoxic environment. Like there's bacterial reactions that cause that particular rock to turn black, and that's the same with coal. And that's why oftentimes we see coal as black, and oftentimes carbon will be black in the rock record. But the reason that carbon didn't get eaten away by bacteria and decompose like all organic materials is that it was in that oxygen deprived environment. And so the bacteria that break down organics like oxygen, and they don't tend to thrive down there. So if you sink something deep enough that's organic and it's oxygen poor, that carbon will tend to not break down and bind to other things or get used by the bacteria. And so it can stick around and be in the rock record. So to sum up here, to classify sedimentary rocks sort of overall, and I think this is a good study tool, so I included it. For the detrital sedimentary rocks, that is the mechanical sedimentary rocks that were pushed around by water and erosion. We've got the clastics, which just mean broken up pieces of things. You can get gravel, which is larger than 2 millimeters. And they can be rounded or angular, and that's your conglomerates if they're rounded, and breccia if they're angular. You can get the different medium grade sands, right? Sandstones made from sand class from sort of sandy sediment. And that's where the quartz tends to dominate. You get the quartz sandstone. If it's quartz with considerable feldspar, so much more red in color or pink or orange in color, we call that an arkose. It's a kind of sandstone, but it's just got a ton of feldspar in it, so it's not that nice clean white or yellow color or gray color, I guess. So any kind of red tinge, we would call it arkose usually. Then you get dark colors with considerable feldspars, clays, and rocky fragments. We call that a gray wacky. That's not in your kit. These two are in your kit. Then you have the different clastic mudstones, and there the clasts are really small, almost invisible to the naked eye, similar to your aphanitic igneous rocks. But here, instead of magma cooling and forming small crystals, this is just really small fragments that have traveled so far that they're rounded down to almost nothing. And these are your shales, which tend to split into these thin layers, or they can sometimes break into clumps or blocks, and that's your mudstones. And shale and mudstone are very closely related, but shales tell you something about the different environments, which I'll talk about, in which they formed. Then you have your chemical sedimentary rocks here. They're grouped as inorganic and organic or biochemical. And here the textures are clastic in the case of limestone, where you can have some noticeable calcite grains in a limestone. Or you can have a bunch of these non-clastic ones like a dolomite, which is your calcium carbonate with magnesium attached, or sometimes just magnesium carbonate. Again, that's dolostone. Then you have microcrystalline quartz, which is your chert, halite, which is rock salt, we call it then, when it's in its rock form. And then gypsum can be calcium sulfite, or pardon me, calcium sulfate, or magnesium sulfate, or magnesium and calcium sulfate. And it's a hydrous mineral in that it has some water in its crystal structure, and we call that rock gypsum. These are not in your kit as sedimentary rocks. So you'll be long done with gypsum and chert by the time you take the test. So don't worry about that. You will not see chert or gypsum on your test, but I'm including them here because they are inorganic sedimentary rocks. Then we also have the biochemical ones. In the clastic case, we have big chunks of calcite and calcium carbonate. That's, again, limestone, which can form from organics. But then you have the non-clastic organics like microcrystalline quartz, again, as chert. And then this one, which is definitely in your kit. This is a non-clastic biochemical. It's from altered or metamorphosed plant remains, and that's your coal. And you should all get coal. It's black. It's super lightweight. It has certain textures. Once you guys get your hands on these, you'll be able to identify it. Coal, I think, no problem. So let's get into the environment of deposition. So this is kind of the second bit of this lecture. I know we're going a little long, I apologize, but this is where we look at sedimentary rocks and they tell us a story about where these rocks formed. And so the clues that we find in sedimentary rocks that tell us about their environment are fossils, obviously. Again, like all sedimentary rocks, class, shape, size, sorting, and composition. And then different sedimentary structures. And what I mean by that is different behaviors of deposition or different behaviors of the way water is behaving as it's depositing these things can tell us something about the environment. So if we use some of these clues to tell us about the existing meteorological conditions under which these sediments were deposited and the subsequent rocks were formed, that can tell us something about the environment in which they formed and what were the surface conditions at the time. And we use this to tell us something about the agents that are responsible for the transport and the deposition of these sediments. We can tell how much rainfall there was or how much wind there was. Was it a fairly calm environment or was it real stormy? These sorts of things. Were there lots of rivers around, and what were the styles of those rivers? Were they fast moving? Were they slow and meandering? Could some of these sediments been deposited in an ocean environment? Could some of these sediments been transported by glaciers or icy conditions? And based on, like I said, the sorting and the class size and the rounding and all that stuff, that tells us something about the environment in which they formed. And in geology, when we talk about ancient environments, we call them paleoenvironments. And sedimentary rocks record these paleo environments and tell us something about the environment at the time of deposition and the subsequent lithification or formation of that sediment into rock. And we break these paleo environments into two kind of broad categories, terrestrial and marine. And we're going to go through kind of a list of these, and we'll kind of identify them as terrestrial or marine. And again, they give clues to the environment of deposition. right? And they can be found in the sedimentary rock types and in the different structures that we see, whether that be something I'll mention called cross-bedding or mud cracks, or whether we see fossils in there, etc. So for terrestrial environments, here's a bit of a sort of surface environment, so on land. And a lot of this will look familiar to you. You know, we've got this kind of fast moving mountain stream here. We've got a meandering sort of, you know, lower energy river. We've got a delta. We've got a lake. We've got glaciers, maybe all kinds of things. So if a sedimentary rock is sourced from the mountain, or sediment is sourced from the mountain, or if it's being sourced and transported in a glacial environment at the tops of those mountains, either that can be transported by a glacier, or sometimes in these mountain environments, some of that sediment will go down in this like steep stream or river. So a real fast moving, high energy mountain river. Sometimes terrestrial sediment can be deposited by sand dunes. Sometimes it can be deposited by a gentle sort of meandering river. We have those all over Michigan. In fact, all of our rivers are gentle meandering rivers. Think the Grand River, the Muskegon River, the Kalamazoo River. So they tend to be, and these tend to be like kind of lower energy, slower current, and so they would have, you know, different sediment types in them compared to you know, a faster moving mountain river. We have deltas. That's where these meandering rivers empty out into a larger body. The classic example of this is the Mississippi Delta, which the city of New Orleans is built on. And I'll get into this a little bit more when I talk about rivers, but that's just where a lot of the sediment that's being carried, that's been sorted from coarse-grained sediment and larger boulders up here, eventually all you have left is that fine-grained sediment, and it starts to fill in this area and deposit these deltas here. We can have lakes. We can have wetlands, another thing we see a lot here in Michigan. And then we can also have marine environments. So here's one of our meandering rivers depositing this delta. But what do we see in marine environments? Well, you can have a beach environment. So that's basically this little bit of land and this little bit of ocean. And really it's about the interaction between the two, right? So still marine. Then we've got a reef, so like a coral reef, any kind of buildup of organic carbonate materials. A lagoon, which is sort of a muddy, shallow region between a beach and a reef. We've got coastal dunes, which can act very differently from inland dunes. We've got tidal flats, which are only partially submerged underwater, but during high tide, water will encroach in there. So very much a marine depositional environment during the times of high tide. Again, we have a delta. You can get offshore deltas where sediment continues to deposit at the mouth of a river into a larger marine environment. And sometimes there you can get barrier islands, which are either sediment that deposits and then is eventually exposed above the surface of the water, or it can be a reef of organics, like a coral reef, that's also been exposed. And then eventually you have the continental shelf dropping off here, and at the bottom of that continental shelf, you've got the deep seafloor, and you get certain sediments that deposit here. So as we're looking at all of these, I want you to just be thinking about what kinds of sediments would get here and what would they look like. And the same for terrestrial. So this is from your textbook, and this is showing the different terrestrial and marine depositional environments that we see. And I'm just going to kind of go through these quickly, but I encourage you to read up on them or ask about them in lab if you want to know more. But you can get sediment deposited glacially up here in these kind of high alpine environments. And those glaciers can either be alpine glaciers or they can run down into continental glaciers, and they transport different amounts and types of material. At the base of mountains, you get alluvial fans like we see in Death Valley. Then you can get playa lakes and salt flats in these flat sort of desert environments. But then as we move into more temperate environments, you can get streams running through these meandering streams. You can get swamp environments that deposit material, as I've mentioned, that some of the real dark mudstones with lots of terrestrial plant life and stuff. Then you can get lagoon depositional environments, barrier islands, reefs, and deltas at the mouths of certain streams and rivers as they run into larger water bodies. And also in that environment, and we live in one here in Michigan mostly, you can get floodplains, and this is where rivers flood and material that is being moved through the river system can overcome its banks, flood into these big valley areas, and deposit sediment there as well. For marine, we have turbidity currents. That's currents that are running down off the shelf, the continental shelf in a marine environment, or you can have deep sea fans that are very similar to these alluvial fans, but they're actually underwater. We can get splits here along the coastline. And then moving up the continent from there, sort of like straddling terrestrial and marine, we can get, lakes and beaches that are closer to the marine environment, estuaries where bits of the ocean have encroached in and up onto the onto land. They kind of look like lakes if you were there, but you'd realize like, oh no, this isn't a lake. I'm actually looking at ocean water. It'd be salty. These are all over, Washington and northern Oregon. And then further in, you can get sand dunes and things like that. But a lot of this stuff is all sourced from marine influence. Like these sand dunes are sand that was sourced from marine environments, but the water level has since dropped. All right, so let's get into sedimentary structures. So I'm going to spend a little more time on this first bullet point here once we get to geologic time and age dating. But I do want to talk about sedimentary beds. And one of the things we want to remember here is one of the fundamental laws of geology, and that's called the law of original horizontality. And basically, in a nutshell, what this law states is that sediments, when they're deposited in marine environments or lake environments and river environments, anywhere where water is depositing sediment, they tend to be deposited in these horizontal flat layers, right? Because this is just water over an area, and sediment is being deposited and it's falling down and it's settling horizontally, right? Just due to gravity. And when it does this, we call these layers strata or beds. And each one represents a pause or a change in the sediment being deposited. So over here on the right, we've got alternating layers of this whitish color, and then the gray color, and then white, and then maybe gray again, and then maybe some pink. Each one of these beds, as you can recognize them, are distinct from each other, and they represent different sediment types. So if you walked up to this and you looked really close, you'd see that some of it might be sand, some of it might be mud, some might be different colored sand or different colored mud from the other layers around it. And then there's thicknesses in these layers that are different from the thicknesses of other beds. And so down here, we can see that these beds were being deposited more quickly with different kinds of sediment types. And then up here, a more consistent, long-running sediment type was being deposited over time before a change. And that tells us something about the sediment being deposited and the activity on the surface. So one sedimentary structure that's very common, particularly in sandstones, is something we call cross-bedding. And this is stacks of beds that are either at an angle or horizontal, and they're formed in environments with a lot of sand and wind or wave action, right? And dunes are an example of this on the surface. You can get cross-bedding in dunes. So you can imagine sand being blown over a dune, and On the one side here, you're going to get a gentle ramp up of the layer. And then when it gets over this certain point in the direction of the wind movement, it's going to drop down, and then it's going to start to deposit, and it's going to drop down. So you get these sort of asymmetrical beds here. And on the surface, it might look like this, right? But as you begin to bury these, or the wind changes direction over time, you get cross beds that run in one direction, and then cross beds that run in another direction, and then cross beds that run in another direction. And the sort of low angle slope part of a cross bed tells you that the wind was coming from that direction and moving towards the direction of no angle or steep angle. And I can talk about this more in lab, but hopefully that picture, if you stare at it long enough, you'll be able to figure out what I mean there. And this is what cross beds look like in the rock record. So here's a ancient beach or dune environment that eventually got lithified to rock. And you can see these little cross sections, this little kind of cutout of these low angle layers here that represent some kind of a dune environment, ancient dune environment. And then when we get to relative age dating and geologic time, we'll talk about what this means here when you have these cross beds that suddenly stop, and then you just get horizontal layers being deposited above it. That tells you something about a change in environment and something about the amount of geologic time that's taken place just between this little layer here. Then we can also get graded beds. So graded beds gradually change from coarse in sediment at the bottom to fine at the top. And they're characteristic of rapid deposition of water containing sediments of different sizes. And this is usually a change in current, so a change in energy loss of a current as it's like a river, let's say, that has a current. If there's a sudden change in energy, you're going to get a change in the types of sediment that are being deposited there based on how rounded they are, how large they are. Because you can imagine a river with a lot of energy is going to be able to move much larger fragments of rock and round pieces of rock much better and transport it further than low energy currents. And so if you see a lot of really large sediment at the bottom of a riverbed, and then all of a sudden it grades to medium or fine grained sediment, that means that the river was really going at first and was able to push boulders out of the way and deposit them further down. But eventually it just went down to a low trickle, right? And once it got to that, it could only move mud or really, really fine sand. And so generally rivers grade from really coarse at the bottom to really fine grained at the top. And here's what a graded bed would look like in a turbidity current, which is kind of along a continental shelf. And so you get a sudden movement of lots of debris as it falls down this shelf. So all this stuff is being pushed. And so you'll get really, really coarse grained. You can imagine everything is kind of falling down very quickly, like an ocean avalanche, just all settling down. And then as more stuff is being deposited on top of that after the kind of avalanche event, it just gets lighter and lighter. So we see this in the ocean too at continental shelves in addition to rivers. And then we can also get ripple marks. So this is when you have current directions, you can get symmetrical or asymmetrical ripple marks. And many of you have probably seen this if you've ever walked along the shore of Lake Michigan. At the very shallowest part of Lake Michigan, as you're walking along, if you look into the sand there, you'll see these kind of symmetrical little ripple marks oftentimes in the real shallow areas. And what that's doing is it's similar to cross bedding on dunes, but in this case it's water, and this shows you that the water is moving sediment in one direction and then moving sediment in the other direction. And this is indicative of currents that move forward and backward, forward and backward. And this is often the sign that you're at a beach environment because you have waves lapping up and waves lapping back down. You'll notice, I mean, unless you go to a really special river, I don't think you'll find a river where the current is changing back and forth, back and forth, back and forth. So this is almost always indicative of a beach environment. And when it's symmetrical, it tells you for sure that you've got waves moving up and waves moving back down. It's just building up sediment along this side and then building up sediment along this side when it changes direction. Here's what symmetrical ripple marks look like in the rock record. We have evidence of this all over the place. I've got a chunk on my windowsill. We see these in the UP. You can find these in quarries in the lower peninsula. But you see that one side and the other side are fairly symmetrical. So they're about the same angle and they're pretty consistent. So this tells you that this sand was deposited in this area at an ancient shoreline, right? So a beach environment. Another sedimentary structure that we see often is mud cracks, and you've probably seen this in like a, mud that gets on a parking lot, and then the sun dries it out, and you'll see these little cracks. You can see this on the side of the road sometimes, but mud will preferentially crack in these kind of polygonal structures, and you'll see that once these structures get buried by other sediment, that form, that shape will get preserved. Sort of like a mold or a cast, it kind of gets held in place, and then that gets buried over time, and then it gets lithified under pressure, and eventually that becomes rock, and then those mud cracks can be preserved in that rock record. And this is, again, as you would imagine, this occurs in mudstone, and it tells us something about the paleo environment here. In this case, we were in a shallow lake or a desert, right, where mud was exposed to the sun, and there was enough change in the water levels that mud that was fairly wet, once the water receded away from it, it dried very quickly in the sun. And so when it dries very quickly in the sun, it forms these cracks. And so that tells us we were in an environment where there was a lake that was either shallow and alternating in depth, or it was a sudden lake or sea retreat from the area. So a sudden change in environment from a sort of marine environment to a desert environment. And then in sedimentary structures, we can also get trace fossils. So these are animal tracks, trails, or burrows. And then we can get actual fossils, which are the remains or molds and casts of the remains of different animals and plants. So let's talk here real quick about how organisms are preserved. So the different types of fossils that we tend to have, you can have actual shells or hard parts that stick around, right? So that's an actual organically sourced mineral that is preserved in the rock record. And so you're actually looking at the actual shell in some cases. We can get bones also, so the skeletal fragments of mammals and birds and dinosaurs, etc. So that's usually, those are the kind of the hard parts that get preserved, whereas all the soft parts like, livers and tongues and other different tissues, that stuff decomposes away, leaving only kind of the hard parts behind to create some kind of a preserved structure in the rock record. But you can also get replacement, and that's where, let's say a clamshell gets buried under a bunch of sediment. That clamshell slowly starts to get pressurized and turned into rock. But then let's say some dissolved mineral in groundwater or in some other process moves through and dissolves that, and then leaves a cavity where another mineral later that's dissolved in water fills that cavity, slowly cools, and replaces that spot with a different mineral. In a lot of cases, that's silica. So you can break down the carbonate stuff that's in our bones, the calcium carbonate stuff that's in our bones, and you can replace it with a silica mineral that comes in later, and it fills that space, recreates the shape of that clamshell or bone or whatever, and then that silica sticks around a lot longer. Remember, because we know silica, namely quartz, likes to stick around on the surface much longer, so that'll preserve that replacement fossil much longer. Then you have casts or molds. This is where a similar process to replacement happens, but something doesn't necessarily fill it in. And so it will leave behind a gap or a void space in which that shell has been preserved, or the shape of that shell has been preserved, or you can get other sediment that comes later once that void space is exposed to the surface and fills that in, and so that can also be preserved later as a mold, no, as a cast. Yeah. Okay, and then you can have a thin carbon film sometimes, where a carbonate organism, any kind of plant or something like that that has carbon, it's carbon rich, will fall in between two layers, and it'll get pressed and pressed and pressed and pressed and pressed, and eventually all that's left behind is a carbonate film of the original shape. And there you're actually looking at the original carbon of the plant, but you're looking at a thin layer of it. Don't sneeze near it, it's going to blow away. These are very delicate, but they're beautiful if you find them, because you're actually holding the original material of the living creature. You can get impressions where, say, a fish died in a mud flat or some kind of area and then is buried by sediment, and it leaves an impression behind, very similar to a cast or a mold. But here you still have a lot of the structures preserved of the actual organism, whereas here you just have the outer thing, like pressing your thumb into a piece of clay, whereas here you've got minerals that replaced and left an impression of that organism. You can have Jurassic Park style, you can have insects and things preserved in some kind of amber, or some kind of organic material that then cools and then can become a rock. So amber is it's not a rock, but it's a sort of preserved mineral, organically sourced, that does harden and can preserve mosquitoes that will eventually be used to make dinosaurs that kill us all. And then you have and then you can also have sort of constructed structures. These are like corals and stromatolites. Sorry, you can't read that very well. But this is where, in this case, a stromatolite, which is a clump of bacteria, will form here, and then another layer will grow on top of it, and another will grow on top of that, and another layer will grow on top of that, etc. And there's enough hard material in these constructions of an algal bloom or a coral where that stuff can also be preserved in the rock record. So this brings us to a very brief overview of some of the nomenclature that we use when we're talking about sedimentary rocks. For some of you, this will just come and go. You'll learn it for this class. You'll never think about it again, or you might. So how does that water get into the middle of a desert and start to move sediment around or deposit sediment on top of it, etc.? Well, at one time, most continents have been inundated by shallow marine seas. And since that happened in the past, we suspect it's going to happen in the future. And we see evidence of it happening in the past based on what we call transgressional and regressional series. So what does that mean? Well, sea level rises and falls based on different environmental conditions. Where are the continents relative to the equator? Is there large-scale glaciation happening that's sequestering lots of seawater up in glaciers, etc.? And so sea level rises and falls just sort of naturally. It doesn't have to be climate change due to human influence. The environment influences climate change and has over time. And so we see evidence of transgressions and regressions, that is, rises in sea level, or transgressions, and drops in sea level, which is regressions, over time. And so when we see that, we'll have something like, let's say, time one here. We have a shoreline, here's some ocean, here's some land, and here's a beach environment. And in this beach environment, you'll notice we're mostly getting sand deposition, obviously on the shoreline, but we're getting sand deposition out to a certain point off the coast, right? And that's just ocean sand washing up, and depositing. Then at time two, sea level has begun to rise for whatever reason. And when that happens, now the beach has now encroached up into this area here. And so it's depositing beach sand. The terrestrial life has receded up, right? And now this area down here that at time one was having sand deposited on it, now we're in a lagoon environment where there's mud being deposited. right? And so we see sand at the bottom, sediment, which will become sandstone. And then we have mud being deposited here above the sand, which will eventually lithify over geologic time into mudstone if this area gets preserved. Then sea level rises even more, encroaching even further up. Now we've got this beach environment all the way up here. It's eroded a lot of the continent, bringing sand down here and mud, right? And eventually we'll start to get a reef forming, and that reef contains tons of carbonates, right? Corals and different organics like that. And so what do we start to get? Well, we start to get calcium carbonate deposits being deposited. And that gets deposited in the form of calcite and limestone. And so where once there was a beach right here and sand was being deposited, then it got a little deeper and it was a lagoon, and now mud's being deposited. Then it got a little deeper still, and now limestone's being deposited. And that means that sea level is rising. Sand, mud, limestone means sea level rise from shallow at the bottom to deep at the top at this one location. So when you see beach sand underneath mud, underneath limestone, that's a transgression. And this is what that would look like in the rock record. So this is a section of rock that was formed during a transgression with older units at the bottom, and then sandstone, some period of lagoon deposition, and then some period of reef deposition. And so, as you would guess, the opposite is true when we have a regression. So here at time 1, we've got the previous sand. So now we're at time 1, but we're really at time 4, I guess, from the previous slide. So these are the depositional units that we saw in the transgression. But now as we regress, we've got limestone being deposited still here at time 1 because it's deep. And we start to see, as sea level falls, we start to see mud being deposited over that limestone. And then we start to see sand being deposited over that mudstone. So we see the opposite thing happening. So here we've got limestone at time 1, mud being deposited over limestone at time 2, and then sand being deposited over mudstone at time 3. And so we see these kinds of structures in the stratigraphic record. And we call these pinch outs, where it comes to a point and then back. Okay? And these tell us something about sea level rise and fall over time. And so this is very important when studying stratigraphy, because really stratigraphy is absolutely telling you the environment and the behavior of the surface at the time of formation, particularly as sea level rise is concerned. And really quickly, this is what regression looks like, where you have sandstone, mudstone, limestone. Okay. So when you're interpreting the sequence of a sedimentary rock, if we had a reddish-brown breccia at the top, it's poorly sorted with angular fragments of granite and a muddy matrix. Then we've got a tan sandstone at the lower part with some broken shells. Then we've got a mudstone here. Then we've got a thick gray shale intervening layers of limestone with different fossils and fossilized coral. Then we've got a tan sandstone, including fragments of shells. And then we've got a red, well-sorted, large crossbed here. And so we'll talk about this in lab, but I want you to look at this, and I want you to kind of come with an idea of what this sequence would be. And we'll call the bottom here time 1. And then this is time 2. This whole thing is time 3, time 4, and time 5. And I want us to think about sea level rise and fall in this sequence and the environment of deposition. So that concludes a rather long-winded sedimentary rocks and sedimentary environments lecture, but super important to geology. You take 5 classes about this when you're a geo major. But I hope you found it interesting, and tomorrow we'll get our hands on some sedimentary rocks, and you'll get to see these things firsthand. Have a good one.